have both build, operate, feed, which is front-end engineering and design, and pre-feed. These feed projects, just to give you a feel, is they're a design paper study, but the last step before you go and do a build, operate. So from our perspective, it's important to kind of go over that entire realm. So you've been involved in the design, you've been involved in kind of putting the pieces together, and now you can move forward to the build piece, and you're engaged in that as well. And I'm going to show you some of the projects that we're involved in later in this talk. So one of the other factors that's critical to keep in mind, that we're very lucky, is we're here in Illinois. And we're very lucky because Illinois actually has one of the best geological storage areas in the world. And it's because of the geology. You have enough porosity that you can get the CO2, down into those enclaves when you inject it. And as a result, our geological survey has done a number of different projects related to geological storage. And this is funded by the U.S. Department of Energy, the DOE. So what I want to illustrate here is you've got a whole series of storage projects, and this is part of the Illinois Basin, which encompasses Illinois, Indiana, as well as Kentucky. So the value of this is I'm not going to capture CO2 unless I can do something with it. And typically, if I capture, I need to store it. So I've got great storage, which means I'm going to have capture projects built around it. And this is important because if you look at the storage and the capture projects, the state of Illinois has the most amount of projects out of the entire US in terms of having both these capture and storage projects. So again, very exciting to be doing research here in Illinois in this area, because it's a perfect place to do it. Now, there's another piece I talked about, utilization, and that means I can store the CO2, or I can take and I can do something with it. And that means utilizing the CO2, and we have projects here as well. So the importance of this, that what I want to share with you, is that we have a whole portfolio of projects right here in the state. Makes it quite unique, which means a very fertile area for doing research and development. And that's why you'll see some of the projects that we've been involved in. That's why we're able to do it. So again, a really big advantage of being in the state and having that opportunity. So let's move on. And I want to backtrack a little bit and ask the question, let's make sure we're all aware and we're working off the same definition when it comes to net zero. And this is very important because I'm sure you've heard net zero quite a bit. We're going to make sure that we're all on the page in terms of defining it. And the other thing I want to emphasize to you is net zero is hitting every industrial sector. Everybody is concerned about it. If you talk to any company in any sector, their goal is to say, we need to get to a net zero target. So what does that mean? And I pulled off here a number of different definitions from the web that talk about a net zero. I, in particular, like this one because it really focuses on if you're achieving net zero, you're balancing out your emissions with the amount of CO2 that you're removing. But it's also important to remember, to achieve that net zero, you want to get there. And in fact, some situations, you might even be able to get net negative. And I'm going to show you some of those situations later in the talk. So I always look at, if I'm going to do this, this is great, but what metrics should I use? And by far, I believe the best metric is a life cycle analysis, or an LCA. And there's a lot of ways to do that. I know some of the folks maybe have done that in your classes. There's 3 different software that we typically use. There's an Open LCA, there's a GREET program, which is used by Argonne, and then there's another software used by the National Energy Technology Lab. That happens to be the one we use a lot because it's required for the DOE projects to use that. But there's a lot of existing LCA software out there, and almost all of our projects you've got to do the LCA, because obviously, does it make sense to do a project if you're actually giving off more CO2 than you're managing and you're preventing from the atmosphere? No. So we have to show that. So with that in mind, let's take a look at when it comes to the LCA. I mean, just to kind of step you through, I want to emphasize that, again, as it said here, you're looking for the full value chain. So that means I want to emphasize you're going all the way back to kind of the raw material. Then you're processing it through, and you're looking at all the way to kind of essentially the end of the life of, for example, a particular product. So here's the importance, and here's an important point I want to leave with you, and that is it makes a big difference what I start with. And I'm going to demonstrate to you, for example, what's the difference if I start with a fossil energy versus a non-fossil energy. It makes a really big difference. And here's where you'll in particular see the advantage of using nuclear. And here's some charts that I pulled down from a report on the web. And I want to first point out this one. You can see here the y-axis is the kilograms of CO2 equivalents per megawatt hour. It's the standard metric that you're looking at. Obviously, the smaller, the better in terms of the LCA. Take a look at the penalty you pay up front just by using either natural gas or especially coal. It's a very, very large penalty. So that means that if I'm trying to achieve net zero with, let's say, my cement plant, it makes a big difference whether I'm starting with coal, whether I'm starting with natural gas, or one of these other options over here. To me, and again, being with the group that you are, I want to point out, take a look at the very attractive numbers for SMR. It really makes you pause and say, wow, there would be a huge advantage of using SMR as compared to these fossil fuels. In fact, it's better than, for example, solar under this case. So keep that in mind. Now let's come down to the chart below. We're now looking at the same LCA analysis. What I'm doing now is I'm going through and, for example, I'm putting carbon capture systems on my fossil plants. When I do that, for example, I want to pull this one out here. This is super critical with carbon capture. This is a coal situation. You can see how I've significantly reduced that overall, the LCA, which is good. I mean, I'm going in the right direction, but still, if I look at it compared to renewables, if I want to look at it as compared to nuclear, still a big advantage when I'm sticking with nuclear as compared to even the capture end of things. So some really intriguing things to look at. I think it kind of gives you some ideas as to the opportunities where to go with nuclear and to go with SMRs and effectively the microreactors. So I think that will keep that thought in mind as we move forward here. So if I'm going to get to net zero, there's not one magic bullet or silver bullet in this case. I have to do a variety of different options. And here's the variety that I'm showing here. And I have to do all of them, I would argue. There's not just one that works the best, because remember, I'm trying to do this across a variety of different sectors. Now, in today's talk, what I'm going to really focus on is talking about carbon capture from point sources and direct air capture. Now, the capture from point sources are large, existing, typically industrial systems. So it could be a power generation plant, it could be a cement plant, so forth. Direct air capture is literally pulling out the CO2 from the air. Sounds like you've heard about that at previous lectures. We're going to be talking about both of those today. So first, let's talk about the point source end of things. And that's critical because, again, that's a piece that you have to do to get to your net zero. So I want to step back for a minute and say, what are the various steps if we're going to do CCUS off a point source? So let's again assume this is some type of industrial facility. The first thing I've got to do is I have flue gas, which is going up the stack. And depending on the process, it could be anywhere from a 3% to a 25% CO2 level in that flue gas. I want to be able to pull the CO2 out of the flue gas. I want to get it to as high a purity as I can, typically a 99% plus purity. Once I've got that, now I'm going to compress it, make it supercritical, because what I'm going to do, I now have to transport that through a typical pipeline, and I'm going to transport that to a geological storage site. So, you know, typical distances here could be on the neighborhood of 3 to 5 miles up to maybe 50 to 100 miles. The key thing is I've got the pipeline. I'm going to do my injection here. And now, once I've done my injection, I have to go in and do monitoring and verification. This is important because obviously I want to see, is there any leakage? Is there any loss of that CO2 that's stored? This is all critical. It's critical, obviously, from an environmental perspective, but also now there's actually financial drivers. You may have heard about 45Q tax credits that you get for doing storage. So this has changed the game significantly, and another driver for being able to do that MMV piece. Now, how does utilization fit in? Remember, I mentioned to you, one option is storage. The other thing is to do utilization. So that means taking the CO2 and, for instance, either using that CO2 to grow algae, which can then be used for animal feed, biochar, biofuels, or, as you'll hear later in the talk, taking that CO2 and injecting it into a concrete or ready mix. And by doing that, you'll actually not only sequester the CO2 in there, but you'll actually make the resulting concrete structure stronger. So some big advantages there. But the overall important thing here to state up front is the most expensive piece to this entire operation is the capture step. 75 to 80% of the cost is driven by capture. So needless to say, there's been a huge effort when it comes to R&D related to capture. A lot of work done in that area. And on the point source side, work that started really in the early 2000s to move this forward. So I want to give you a little bit of a feel for what that looks like. So let's say I want to do a capture process. How can I do it? And for those of you who are involved in the materials end of things, I think you'll really relate it to this, because the material science is really strong here and really critical, because there's really right now 4 different ways that I can do point source capture. By far, the most common one, and the one that's been developed the longest, is solvent-based systems. Typically amine-based solvents, which have been used for years in other processes, such as cleaning up natural gas and stuff. These are proprietary blends of amines that are used for this process. So the chemistry behind this is very, very key. Also then, kind of a similar process is the sorbent-based process, difference being it's a solid rather than a liquid. Also membranes, which you may or may not be familiar with, another important factor when it comes to driving the separation. And one of the newer ones is a cryogenic process, whereby cooling down that flue gas, you're able to get the various components to drop off. So 4 different options. They're all being looked at. Some work better than others in certain situations. And I think we're learning all the time as we start to do large-scale deployments of these systems. So there's a couple critical factors no matter what way you do it, and this will become important later when we start talking about how nuclear could play, is all of these require either the use of steam or electricity. You need both of those because obviously you've got to run the capture facility. and you need some type of power to be able to do that. And needless to say, the lower the power, the better, because we talk about what's the parasitic load. So how much energy are you going to need to run that capture system? That's going to obviously impact your OpEx as well. So it's critical to keep it low. Also, we're typically talking about retrofit applications. So that means just before that flue gas is going up your stack, that's where you're going to tap in, take that flue gas, and send that over to your capture system. And as those 2 points below, it used to be, I mean, when I first got started in this area, everything was about power generation only. Now it's all applications. So we've got projects in the cement area, iron and steel. There's interest from the chemical industry, refinery, even pulp and paper. So everyone is looking at this. If you have a large industrial source, they're asking the question, can I manage my existing emissions by using these capture systems? So very critical. So let me take you through a couple examples for each of these top 4 processes. And in some of these are projects that we're working on as well, and I'll talk a little bit more about that. In the first one, as I mentioned, the most common one is the solvent-based process. This is all about actually the largest capture pilot in the world, which is going on over at City Water, Light and Power in Springfield, Illinois. If you drive up 55, you'll see CWLP stacks there. CWLP provides the clean water and power to the city. And if you get a chance, you'll be able to see the actual system will soon be built up on that. This is a process flow. This is a process flow diagram for the process. It's a Linde BASF solvent-based system. And bear with me for a minute because I just want to take you through a few of these things. First, you've got the flue gas coming in from the facility itself, and we run that through a pre-scrubber, also called a direct contact cooler, which will knock out the CO2 levels. It's important to get those down because the amine solvents are sensitive to that. Then we go over to an absorber, and it's in the absorber that all the action occurs. We have the flue gas, which in this case is about 11–12% CO2, the rest nitrogen. The solvent will preferentially pull out that CO2. It will chemically bind with the solvent. The nitrogen then will be sent back up the vent that will be vented to the atmosphere. And then once we have the CO2 rich stream, we're going to come over to the desorber or stripper, as it's called, which will then heat up that solvent so that we can essentially strip off the CO2 from the solvent. We'll recycle the solvent, and now we have high purity CO2, typically 99.9% plus purity, which is great. We also target to get anywhere from 90 to 95% capture rates. So an exciting project that we have going on. We have finished the civil work for that. This is a 3D rendering of what the structure will look like. And actually next month, we'll be starting the vertical build. So we'll be bringing in these columns, the DCC, the absorber, and the stripper. So those will be coming up very soon. Everything in green is going to be starting to be put in place in the December timeframe. And I will offer, if anyone wants to go over and see that system, we can arrange for some tours. I think it'll be really cool to watch that whole thing be built. And again, it's a groundbreaker, the use of this new technology, which is much better than the other previous solvent-based technologies. So, and let me, on this particular technology, leave you with the thought, this is what it's going to look like. Here's the plant. You may remember, here's the silhouette of President Lincoln. Here's where that unit's going to go. And the factors that you've got to think about when you're building this is, you know, how are you going to tie into the plant? You need to be able to put in ducting to bring the flue gas over. So all of these pieces are now in place. And like I said, within a month, we'll start the vertical build. This whole unit should be completed by either May or June of next year, which will have our ribbon cutting ceremony. And then we'll be starting into actually running some operational tests on that. We have some R&D tests that we want to run to demonstrate how well this system can work. So great example of a solvent-based system. Now, I talked about there's other ones out there. Let's talk about sorbents. Again, for those material science people, this should be exciting for you because in the sorbent area, one of the big things is metal organic frameworks, better known as MOFs. Those right now are the material of choice if I'm doing a solvent or a sorbent. So this is an example of a typical MOF. And as you can imagine, these pores are tailored to be able to selectively allow the CO2 to go through it. And to also help it along, it's hard to see here, but these are actually amine groups. So you have amine functionality on these pores, which will again make it much more selective to CO2 as compared to the nitrogen. So now we're going to use these types of structures in a solid form. How does it scale up? A company by the name of Savante has been a leader in this area. And here's, if you go on the web, you'll see one of their systems which they've used. And this is a rendering of what that system will look like to be able to do solvent-based capture. So now we've done solvent, we've got sorbent. The next one is in the area of membranes. Here is a membrane. MTR is one of the companies which is a leader when it comes to membranes for carbon capture. In fact, they're having this is being installed at the Wyoming integrated test facility. Here's the process flow for that system. And you'll see again, you've got your flue gas coming in. This is a two-stage system where you have a membrane here, which is you're pulling a vacuum on. You're going to essentially create a CO2-rich stream here, which you'll then send through the second membrane. And it will be at this stage that you'll get your CO2 coming out. And then you'll, again, go through the process of pressurizing it up to reach supercritical conditions. Here's a rendering of what that unit will look like. This is targeted to be 140 ton a day large pilot unit. So another approach, in this case using membranes. But again, keep in mind, like even with this, you're going to need to run the pumps to be able to do the vacuum pumps, the compressors, everything else for this process. So we've done solvents, sorbents, membranes. Now we have cryogenic. And one of the projects we're engaged with is a process, Air Liquide's cryogenic process. It's being used at the Wholesome St. Genevieve cement plant, which is right across the border in Missouri. And this plant is very interesting because it's the largest single kiln cement facility in the world. And therefore, you could see significant amount of 4.5 million metric tons emitted per year. So being able to capture off that is really key to be able to do. Here's a picture of the facility itself. For example, what we're looking at is putting the capture facility down in here. And here's an outline of the Air Liquide process. It's a two-stage process where the flue gas is coming in. I do a pressure swing adsorption step where essentially I now get a stream which is enriched in CO2, which then I can send over to the cryogenic process labeled cold box. And it's through that I'm able to get my high purity CO2 and able to get 90 to 95% capture rate. So lots of different options here. There's a lot of advantages and disadvantages. I could give a whole talk about that. And again, depending on your process, you might go with one versus the other. So exciting opportunities there. But now, as we've talked about point source, the other area is direct air capture. And this is becoming very important because in direct air capture, I'm literally pulling down the CO2 from the atmosphere. And why is this important? Because on point source, I'm preventing more CO2 coming out. But if I want to pull down the existing CO2, I need to have direct air capture or DAC systems to do that. Now, from the material science end of things, it's typically solvents and sorbents. And guess what? Many of those solvents and sorbents are very similar to what you would do with a point source type of system. So you may have seen this before, but here's, again, really simple how the DAC system works, where what I have is I have a blower, which is bringing in CO2 from the atmosphere. That's, in this case, I'm showing kind of a sorbent-based system where I'm absorbing the CO2 onto that sorbent. Now, that's kind of the step one. Step two is then when I reverse the process, and now I have to go in and I have to drive that CO2 off of this sorbent. And I do that by typically heating up that filter. And in this case, it's talking about 100 degrees C. That temperature varies a lot depending on whose technology you're talking about. So the important thing, though, is no matter what temperature that is, you need to be able to heat that. And as you can see that, if you're going to do the heating, you want to do it with either a renewable power source or you want to use waste heat, because either of those are attractive from an LCA perspective. If I went in and used, a coal-based system, that would not be a good way to do it because I'm going to take a big penalty. So very important to keep that in mind, because the overall LCA is this is going to be very important. Obviously, just like with point source, once I have this CO2 stream, now I can compress it, liquefy it, pipeline it over to where I'm going to do the storage, or I can utilize it. I've got a lot of this downstream structure is going to be the same, whether it's point source or DAC. And that's a huge advantage because, now I can leverage that existing back end structure. So now I'm going to talk a little bit about some specific projects that we're in the process of running. One of them is with a company by the name of Climeworks. They're one of the leaders in terms of doing DAC structures. This particular project, one of the unique things is with DAC systems, unlike point source, it is very sensitive to the climate. So this project was designed so that we're looking at 3 different climates from California, Louisiana, and Wyoming. So we want to see the impact of climate. And the other thing we wanted to look at is how are we going to effectively heat and remember that phase 2 where we're going to drive off the CO2? And in this case, one of them is geothermal. The other one is looking at solar, and the other one is looking at the use of waste heat. So that was the goal behind this. Look at 2 factors, look at climate, and take a look at what's the difference of using different sources to be able to pull off that CO2. Now, like before, now I've got to be able to design the system. Climeworks has right now one of the only operational DAC systems in the world. It's in Iceland. It's called the Orca project. That is designed to capture 4,000 tons of CO2 per year. This is the system shown here. So then a part of this project was to say, how would that scale up to being able to do 100,000 tons a year? And here you can see some of the different options that were looked at. And this is a critical factor as you're going through and scaling these systems. So great progress, very, very important to show that you can scale it up. And needless to say, when you do that scaling, there's a lot of important engineering design considerations to take into account. And then a quick summary of the results to date. This project is still underway and just in the process of being finished up, but it gives you a little bit of an idea how here's the net CO2 removed for each of those situations, gives you the amount of acreage. One of the critical things for this is they found that they could use the same design independent of where they were located. And that's really important because you'd hate to have have a different design depending on the climate and so forth. Here's the results that you're looking at. The other factor that was also important is the relative location to storage. In these cases, there was storage close by, which was a major advantage. Here, you had a very long run to get storage. So that drove, which different option you could go with here. So some of the results shown here, for example, interesting to see that the important factors is, number one, I could use the same design for each one of these 3 locations. The other one is, in this case, it actually seemed to work better in cold and humid conditions. So again, that would be a function, in this case, of the material properties of the sorbent. So, okay, so we've got that project. Now, another project that we have related to DAC is the question of, okay, I can take the CO2, and again, I can store it geologically, but what if I'm going to utilize it, and how would I utilize it? And we have this project we refer to as a DAC-U project, and it's going up in the Chicagoland area, and we're in the process of doing a feed for that. And that means taking waste heat from the U.S. Steel plant in Gary, Indiana. We have a direct air capture facility, in this case, Carbon Capture Inc., another separate company. And then with this situation, you're going to capture the CO2. And here, we're actually going to truck that over to a Ozinga ready mix facility, which is your concrete facility, and use the carbon cure commercial process to inject that CO2 into the ready mix. So very exciting, because we're looking at a number of factors here of not only designing the capture plant, but we're looking at the whole value chain and what impact it has. That this system is being designed for 5,000 tons a year. And the other important thing is, it's not just looking at the technology. We're looking at job creation and regional economic development, environmental justice features. And this is really important, because what I want to emphasize to you is, in all these projects now, we're not just looking at the technology. We're saying we want to make sure that there's benefits to the community. We want to make sure that there's benefits, especially to disadvantaged communities, EJ communities, and so forth. And that's going to be a critical factor as we go through and execute this project. Here's really quickly some of the results up here. This is an outline of the carbon capture Inc. process, is how they go from the sorbents itself all the way to modules, clusters, arrays. Well, right now, if we come down here and we look at the kind of the module phase, this gives you an idea, and you'll see some similarities of this design to the Climeworks design, but also some major differences. So this is some preliminary renderings of what that's going to look like, with these being the intake fans, and obviously these containers over here will have the various sorbents. So remember, the critical factor here is we're using waste heat to drive the process, the phase 2 of the process. So one of the work that we're doing right now is, how do you pull off that waste heat? And these are stacks. So we're going to be at the steel plant. Here's some designs on how we're going to pull off that waste heat and send that over to these DAC systems. So obviously, we're in the middle of doing that right now. The project is coming along very nicely, and we're working on all phases of that. Now, I talked about how to design the system, the direct air capture system. The other question is, what about back at the plant? How do you inject CO2 in? And that is using, as I mentioned, the commercial carbon cure process, which is shown here. Now, the important thing about this is, here's a reference. This is some work that was done that demonstrated that there's a real value in being able to inject the CO2 into the ready mix. And the bottom line, what I want to point out here, at least from this publication, they not only talked about achieving a net a net zero, but the potential of getting to a net negative. So it looks very attractive from that analysis. So hence that's where Carbon Cure has been going in and doing this. And the other big advantage is if I looked at the control system versus this is the control with CO2, you can see an improvement in the compressive strength by using this injection of CO2. So what's the impact of that? That means either I can have the same size, get better compressive strength, or I can essentially reduce the amount of cement I'm using so that I can still meet this level of compressive strength that I need. So it gives me a lot of, from a final end user perspective, a lot of options to go. So it looks very attractive to be able to pull the CO2 out of the air and then utilize it in these ready mix applications. So we talked about point source, we talked about direct air capture. And I think now one of the exciting things as part of this Inflationary Reduction Act funding was the formation of direct air capture, or DAC hubs. This will really accelerate the whole DAC process. And one of the unique things is UIUC not only won one, they won 3 hubs. So we have 1 hub in Florida, 1 in Colorado, and 1 right here that encompasses the Illinois basin. And I'm going to talk today, I could talk at length about all 3 of those, but I'm going to focus on the one in the Illinois basin. And of course, one of the neat things is, remember I told you, whether I'm doing DAC or point source, everything downstream is the same. So if I've got this capabilities, and remember I showed you that before, all these storage projects going on, I could really build what I'm going to say a community around this. So I talk about kind of building a community, designing a community, because I know where that storage is going to be. And there's a lot of storage capabilities here. And again, this outlines for you very nicely where exactly that Illinois basin is. So if I know that, I know where storage is. We're working with NCSA on this. They're using some great techniques to be overlay a whole series of GIS data that will enable me to go in, and I talk about now a DAC master planned community. Because I know, for example, here's my storage sites. Here's, for example, some potential sources for renewable energy, solar in this case. I also know, since these processes will need to have water, this gives me an idea of these small blue dots of where the water sources are. Often I'm going to need to have access to an electrical substation. I know where that is. So I've got the whole host of factors that I need so I can design these DAC systems so they're as close as possible to the storage, they're close by to renewables, they're close by to water sources. That's what I really want to do, because the other factor is I not only want to make sure I have water, I want to make sure I can minimize CO2 transport requirements. And this other very important bullet point, I want to also know where are the EJ communities, also where are the opportunity zones. These are HUD opportunity zones, so that then I can understand where those are, reach out to them, and I want to make sure that I'm going to be providing benefits to those communities as well. And here's a map which is just completely focused on where the EJ communities are within this region. So we've got a lot of factors that we're looking at here, and we're hoping that we'll be able to get this project going roughly. We're waiting on the contracts from the DOE, maybe in a January, February timeframe. So again, it's really exciting to be able to do these types of projects, because we're defining the whole CO2 value chain, and we're also really looking at how's this going to fit into being a community itself. So as I come to conclusion, I want to also tell you, when you're a leader, when it comes to net zero, there's a lot of international opportunities. because I mentioned before, people care about how can I get to this net zero. And here's a great example. Here's all the different states that we're working in the US. And as a result of that, one of the leaders when it comes to net zero over in Europe is Teesside University. Teesside University is engaged with a project called Tees Works, which is shown here. Tees Work is kind of in the northeastern section of the UK. It's a place where it was typically heavy carbon-based shipbuilding, cement, steel. And now you can see the exciting thing is they're targeting by 2040 to have this be a net zero industrial cluster, which will be one of the first ones in the world. So we reached out to them. They've been over to visit us. We've been over to visit them. This is their new building that they've constructed as well. And I can announce that literally as of yesterday, the memorandum of understanding between the university and Teesside has been executed. So this is in place. The exciting opportunity here is we have plans to exchange researchers, to exchange students, have joint research together. So it'll fit in very well because they're the leaders in the UK, we're the leaders in the US, and this exchange will, I think, benefit everything from an educational perspective to a research perspective. So very, very fertile ground there. So that's one piece. The second piece you should be aware of is our own Abbott power plant here has been a leader in quite some time. For example, they were one of the first to have what's called a flue gas desulfurization unit. And they put that in place. They brought in industries to be able to see how well it worked. So they have a history of being a leader. Also, many of you, I'm sure, from the Big Ten from football. Well, there's also a Big Ten when you start talking about the universities and decarbonization. And we are a leader in the Big Ten. I know doing a little bit better than we're doing in football, but we are a leader in that. And that's very important because of these factors and this leadership that Abbott has shown is now Abbott is part of the International Carbon Capture Test Network. And as you can shown here, it touch about just about every place in the world that's focused in this. And the whole idea is to really be able to share knowledge when it comes to carbon capture. And this is important because it's a global issue. We want to really address this in the best way possible. And it's exciting to be able to announce that we're part of this network. It's a really, really key piece. So we're an international leader. We're a leader when it comes into nuclear. We're a leader when it comes to carbon capture and storage. I'm going to throw this out as an idea. It's a starter. And remember, I talked about at the beginning, the premise was the idea of having a hybrid type of structure where you combine either point source with the microreactor or direct air capture with a microreactor. Now I'm going to get more specific and say, I would suggest starting with combining DAC with the microreactor to create that hybrid. Do it down at Abbott Power Plant, because obviously that's where the microreactor is going to be located. It would be part of our existing Illinois DAC hub, so that would work out really well. And what I would suggest as first steps is doing a pre-feed. And in that pre-feed, you'd look at obviously life cycle analysis, techno-economic analysis, where would you tie in? And also, again, I'm a big believer as you want to look at the full value chain. So obviously you could take the captured CO2 and you could truck it to storage sites, but what about using it here on site? You know, there's a lot of places for agricultural uses, for example, that you could use the CO2. I think this would be I think a real exciting study. I throw that out as a straw man. Obviously it's not the final solution, but I think what it would result is a really slick type of a deal where we would be the first place in the world to combine a microreactor with carbon capture and then utilization. And the neat thing is, what a fertile ground to do future research. And having it all here with the university, we can control all those pieces and really look at fine-tuning and understanding how these components can better come together and therefore continue to be a leadership when it comes to net zero. So before I wrap up, it's really important to acknowledge the funding from the Department of Energy from this. There's a list of the various grants that they've provided, the projects that I showed you earlier. It's through them, and I also want to acknowledge the importance of the Inflationary Reduction Act, the BIL that passed. All of those have made a big difference, and I want to acknowledge that and thank everyone who's been involved in those projects, and especially thank you for listening, and I'd love to field some of your questions either now or later. So thank you very much.
Dr. O'Brien, that was extremely comprehensive. Thank you very much. We're on top of the hour. We maybe have 1 minute for a question or a comment. Sam, please state your name and your question.
Hello, I'm Sam Dotson. I'm a grad student in NPRE. Thank you for your wonderful and engaging presentation on carbon capture. I have many questions. I'll pick one. It's about the moral hazard associated with carbon capture.
Mm-hmm.
You have two examples of applications, right? Like the point source versus the you have the point source and you gave the direct air capture.
Yep.
So looking just at the point source, if we retrofit carbon emitting processes,
right,
plants with a carbon capture device of some kind, right? You gave
yep.
several examples. Could this reduce the motivation to find a non-carbon emitting alternative process maintain that carbon emitting plant, even though we should be moving away from those processes? Would that retrofit reduce the motivation to find those substitutes in order to recover the cost of making the retrofit in the first place?
Good question. People ask that a lot. The short answer is no. And the longer answer is people are doing this. They're not saying, well, you know what, I'm just going to stick with my existing process. I'll just put capture on it. Everything will be fine. No, they are already looking at other options, but those options are far, far away now. Like the cement people that we're working with, they're looking at other options other than fossil fueled systems, but they're not there yet. So they can either wait for that to happen because they're not going to shut down their plant. We all need cement, so they're not going to shut that down. But they also want to make sure they are dedicated to, they want to reduce their emissions. So this is a way that will enable them to reduce their emissions. The people that we've worked with, like, for example, a shout out to Wholesome, they really, they're very impressive because they have gone through, they have a whole strategy literally driven at the sea level of being able to achieve the net zero targets. They've been very thorough. They've shared that with us. So it's not like they're going to stop with this, but this gets them with their existing facilities better than just staying with what they got. So the answer is this work's going to go on, but it's not going to stop everything. It's in the process as we develop the other items as we go along. And the reality, here's the, I think for all of you, the slick thing, people are now looking at the economics, the TEA, but they're also looking at life cycle analysis. So right now, it might be okay with your life cycle analysis to be in the positive, but people know long-term, they're going to have to at least be down to zero. So that's going to drive you to kind of go the other routes to be able to go there. So I actually am a bit jealous of all of you in this room, because I think if you stay in these areas, you are going to have some very fertile research that you can have a major impact on. So I think I want to leave that to all of you, because all of you need to be very successful, because I'm hoping to hand this stuff off to you and that you'll take your new ideas and fine tune this even more. So
Sam, you said you had 12 questions. No, but I wonder, just to be respectful of our guest time, can I ask if there's, thank you very much for that question and for the brilliant answer. Just for everyone's insight, Dr. O'Brien agreed that our students in our master's degree students will be working on exactly this project. The microreactor plus the DAC project starting next year. So we're very excited about that, our MN students. Any other questions from anyone or any comments? Let's try and wrap this up. Maybe the last question or comment. Just your name, please.
My name is Akhlaq. So I'm also an NPRE grad student. So what is a substantial amount of carbon dioxide emission that is like we must look forward to removing? For example, there are a lot of processes that release carbon dioxide. I was looking at desalination, nuclear desalination, and for that, the carbon dioxide release is around 1,700, 1,800 tons per year. And there are Climeworks modular units, like the Okra that has 500 tons per year, 8 units. So is such a unit of 500 tons per year or even smaller, like beneficial? Like, is that a substantial amount? What is the figure?
Sure. Yeah. So good question. On the point source side, if you talk with, for instance, if you're going for DOE funding, the typical limit's about 100,000 tons a year. If it's less than 100,000 tons a year, there's not much of a drive to do that because the numbers are kind of low. And the reason being because there's so many things that are 100,000 tons or greater. If you can do those, now you can more faster, if that's a word, have a big impact. I mean, you saw the numbers, for instance, for the cement plant, for one of the power generation facilities, the Prairie State Generating Facility, we did a feed study on that. For one of the units, that was roughly 8.5 million tons a year. So that gives you an idea of those are huge targets to be able to reduce the CO2. Now, remember with DAC, so it's also important, gee, wouldn't you like to have larger DAC systems? The answer is yes. But remember, point source, we started developing in the early 2000s. So it's we're 20 years down. We've done a lot of work. DAC systems, I could argue it's maybe 5 years. In a sense, maybe only really 3 years that we've been moving along. So it's not as mature. So hopefully, and again, I look out to the people here, I bet that at least 1 or 2 of you will have an impact on the DAC systems because, again, a very fertile ground to look at making impacts on. And again, here, you've only got, in terms of operational, 4,000 tons a year. So, and clearly, we got to scale that up even more. These DAC hubs, the plan is within a 10-year time frame, you have to be doing at least 1 million tons a year. So that shows you where we want to go with it. It's just DAC's a little bit less mature. So
thank you very much for that question. I think we'll have to call it a day. Clearly, there's a big job ahead of us. We need to draw down around about 21 million tons of carbon dioxide a year by 2040. We're going to need this technology. Dr. O'Brien, thank you so much for giving us a glimpse of the world that's coming and the world that you helped generate.
appreciate it.
It's really, I feel very proud to be an Illini, to be living in the state. I hope you are too, where really big things are happening that are leading and changing the world. We've got a major problem on our hands. We need to decarbonize quickly. We're going to need really clever solutions that we can implement quickly. Dr. O'Brien, we wish you the very best with your initiatives. We're looking forward to continued collaboration with you. And please, just a final round of applause for Dr. O'Brien.
Thank you. Thank you very much. Appreciate it. Thanks. Appreciate it.
I'd like to thank the students and the staff and the faculty for joining. Well, actually not staff, the faculty. Thank you very much.
Well, I'd be excited.
So much to cover.